You're listening to China Manufacturing Decoded from the Sofeast Group.
Hello and welcome to episode number 248 of the China Manufacturing Decoded podcast. This is Renaud from Sofeast, and today I'm going to be speaking with Paul Adams, the head of new product development in our company. And what are we going to talk about, Paul?
Hi, Renaud. Thanks for having me back. It's always a pleasure to be on these podcasts. So today I just want to touch on, or we'll be discussing something that is an alternative, let's say an alternative manufacturing process for metal, and that is metal injection molding, or commonly referred to as MIM, M-I-M.
Right. So this is sort of a less well-known and less common type of metal forming process, not really, metal machining process, one could say. And this is, let's say, in a continuation to your recent podcast episode from, when was that, 3 to 6 months ago? I'm not so sure, but we'll link to that in the show notes. You talked about the various metal machining processes not too long ago. So, and we did not cover MIM, metal injection molding. So let's do that now. And first, to put it in context, if I need some metal parts, right? And typically let's say I'm developing a new product. I need to get some custom parts. So maybe my mechanical engineer is going to design some parts, going to say, well, this should be in metal for such and such reasons. Okay. Then we need to wonder how to make these custom made metal parts, right? So what are usually, just at a high level without going into the small details, what are usually the main alternative processes?
Well, yeah, let's touch on that. Like I said, I don't want to go over things that we've already discussed previously, but from a holistic point of view, as a top level, casting is obviously one of the top sort of processes when it comes to relatively complex geometries and shapes. And in there, you've got a number of different processes under the casting umbrella. You've got sand casting, high pressure die casting, low pressure die casting, investment casting. So that's the obvious one to think about. But and again, it all depends on the application and the shape and the design and what the actual product's going into as an end product. Forging is another process that we can look at. You've got drop forging, hot forging, cold forging, and each of these processes has its own speciality area to be used in, and there's a lot to take into consideration. But so forging is another one. Another top of the mind really comes to machining. And when we're talking about machining, we're talking about, CNC machining centers like 5, 6 axis machines, 3 axis machines, perfectly okay there. You've got drilling machines, we've covered this previously. We've got grinders, we've got all sorts of different machines for completing relatively a broad array of different shapes and surface finishes. So you've got that. Another one, depending on what the material you're looking for and what the shape and the complexity and geometries are of the product, you've got sheet metal forming. Okay, well, this is basically, it says what it does on the tin. You're forming a sheet of metal into a relatively complex shape, or sometimes a relatively simple shape. So that's another one. If you've got a continuous profile on a shape, right? Another really good method to move towards and look at is extrusions. Now, if you're looking at window frames, for example, or some sort of framework, then extrusions really come into their own. And the other one is additive advantage or additive manufacturing, which is basically the MIM side of things, which is what we want to cover during this podcast. So from a top level point of view, we've got a number of different options as a designer that we could look at if we've got a metal part in front of us.
Yeah. So just to make sure people get it. So casting, basically you have molten metal goes into a die, a kind of mold, right? And then cool down and solidify. All right. And this is different from what we're going to to be talking about, or what we're going to be talking about, is closer to the way most plastic parts are made, right? Forging is quite different because it's like banging metal parts, right? Like forming them and then banging them into shape. Machining is done very often after casting or after forging anyway. The parts very often go first into casting or forging, right? And then the level of precision is often not really there, the level of surface finish and so on. So doing some milling and some lathe and drilling and so on is quite common. So sheet metal, it's for things that can be done with, let's say, mostly a uniform, how to say, a metal sheet, starting from a metal sheet of uniform thickness, right? Actually, there's a lot of things done that way. And then extrusion, yes, like think of long form, like typically extruded aluminum is very common. Okay.
Exactly.
And now we're going to look at metal injection molding, which is sort of a way to avoid casting, because casting has a lot of disadvantages, as we're going to talk about. And also, as it comes out, there's less of a need for CNC machining. Would that be a correct statement?
Yes, basically. The amount of post-processing from a tolerance or a finish point of view is a lot less than with some sort of die cut or a cast sort of product itself. But the actual process is very different from casting. Very different from casting. And so the metal injection molding is really, it's not a play on words. It's exactly what it is. It's an injection molding process using metal compounds. And I think if anybody's listening and is fully aware of what an injection molding is and how the process works, is basically very, very similar to what we're talking about here, with a few additional steps that are required for the MIM process itself.
Right. It's not as straightforward, if I may say that. Like, plastic injection molding can be very complicated, with very complicated tooling and side actions and so on and so forth. But sometimes it's relatively simple. Okay, it's a shape that is easy to demold. Basically, you have your mold. You have a barrel that heats up the plastic polymer. It is pushed in relatively high pressure into the mold. The mold closes, and the molten polymer goes all over the cavity, and then cools down and solidifies, and then it's ejected. There's no other major step that needs to be taken into account. Again, in a relatively simple plastic injection molding process, where the part doesn't come with very complex geometry, etc., etc. Okay. What about metal injection molding? You kind of alluded to the fact that it is a bit more complicated, right? There's a few more steps.
There is, yeah, definitely. But keep in mind, when we're talking about this, the injection molding machine and the process, with some front end and back end stuff. So let me talk about the front end. In particular, it's the polymer itself, or what we call is the feedstock. Now, obviously, we're talking about metal injection molding, so consequently, the feedstock or it's not the polymer. It's a mix. Okay, so it's a fine powder mix of metal with a binder. Now, that binder can be a wax or even a polymer that is sort of low temperature melting. So it's got a premix of this pre-stock or feedstock that is used in the injection process. Okay, so that's the first important aspect that is different. Instead of just using the base polymer, which has thousands of different variations, as we all know, you've got to be very careful with respect to mixing your powder with the desired metal, which we'll go into sort of shortly, different types of metals that can be used, and the actual base carrier or the binder that is used in this feedstock itself. So that's the first step.
So if I understand, so the finished part is going to be made in metal, a certain type of metal. However, the the material that goes into the injection molding machine is the metal plus some other materials that will then be removed at some point, basically.
Correct.
If I really summarize. Okay, so that's
correct. That's it.
So step number one is to mix, to get the right powder with the right mix. Okay.
Yep, correct. That's definitely it. So the next part is our standard injection mold process. So we've got our pre-mixed feedstock. Let's call it feedstock instead of a polymer. So the feedstock is then processed exactly the same way through the injection mold. So your tooling would be very similar. If you've got a sort of relatively complex thing, you still need the lifters and the sliders in order to create various different features within the part itself. So all of that is still the same. There is one old sort of change that is generally required. And if you're using injection molding process specifically for one machine, you would generally tend to upgrade to a dedicated hardened barrel and screw. Okay, particularly on the screw side of things, because this is a very aggressive, hard, because it's got the metal sort of elements in the feedstock itself. If you're using a standard injection mold setup, you will wear out your screw very quickly over a shorter period of time, let's say. So generally, everybody tends to go with a dedicated screw, and sometimes the barrel itself does get that upgrade for the metal injection molding. But everything else is basically the same. So we've got the same parameters that are going into the machine. We've got the preheating of the tool, the injection time, the making sure the cavity's filled correctly at the right temperature. We've got the cooling period, the holding period. All of the parameters there are basically the same process of what you would go through with a standard injection mold machine. Hence the injection process.
Yeah, by parameters, you don't mean that the parameters actually are the same, right? The temperature, the pressure, the time, etc. Obviously, these are adapted to this process and to the feedstock and so on. What you're saying is that the inputs to the process, the equipment, the variables, etc., to take into account are basically the same. And the process steps at this stage, in step number 2, again, step number 1 is to get the right mixture of the powder. You put it into the barrel, it gets heated up. It's already some kind of molten. It's not really powder, right? It's some kind of soup, let's say. And then it gets pushed into the into the mold that closes, etc., etc. All of this is the same as plastic injection molding, right?
That's right. Yep. And when the part is ejected out, right, this is where things take another turn as a difference. So originally, you remember we talked about having that feedstock or the premix having some sort of carrier along with the metal component or the metal parts. Well, that needs to now be removed. Now we've got the injected part. We now need to look at what we call debinding, generally known as debinding. And this debinding process is where we generally heat up the part, okay, so we can dissolve the binder, whatever that binder is, whether it be wax, whether it's low temperature polymer, or sometimes that could be sort of stripped out with a solvent or some other process, some other chemical process that is used to remove the binder. So we've removed all of the binder, and you can imagine we've now got a relatively porous component in front of us, and they generally call this as a brown part or a green part. It's not the actual final part that we're going to be working with. If you're going to put this, if you think you've got your final part and you put that into your product for testing, or one, it won't fit because it's oversized, and two, it has none of the mechanical properties that you're actually looking for. So it's really important that we understand this debinding part is purely taking out that carrier that we had at the start with that mix.
Okay, so that's step number 3.
Yeah.
So what are we left with, basically? We remove the binder. What's left?
The really, really important part. The really important part. We need a high temperature furnace, Okay, we're not talking about high temperature, again, depending on what material that we're using, but generally, yeah, if we're looking at some of the stainless steel or sort of some of the high grade sort of steels that we're using, we've got a high temperature furnace, 1200 degrees, 1500 degrees, something like that. And basically what this does, if you can imagine your very small styrofoam balls or some stainless steel ball bearings, okay? And if you can imagine in your mind all of those ball bearings built up into the shape of your actual product, they're only touching on certain points of the sphere. Okay, so what we need to do now is melt. In essence, what we're doing is melting the surface of each of the contact points such that they bond together. So each of the spheres of the metal in the powder, the metal powder, is bonding together. So on a molecular structure, as it were. So everything is coming together, and that's making a really solid sort of structure. Now, bearing in mind what's happening here is each individual sphere is bonding to its neighbor on all axes, and consequently it's shrinking in size. As it's shrinking, right, it's getting a stronger bond because of the surface. Instead of being a point contact, it goes into a flat contact point. You can imagine in your mind what's happening here. That shrinkage rate is huge compared to injection molding. So as you take an injection mold apart, we're talking about 1% or 2% on some of the polymers that we use. Up here, we're talking potentially 16 to 20% change in dimension.
Wow.
That's just really, really big, huge.
Yeah.
So, this is what I'm saying. Once you've got that part out of the injection machine, out of the tool, it's going to look very, very different to the final part. So, and in general, some of the ones that we've been looking at is a 16 to 20% reduction in size. Now, once that's done, that should be relatively stable from a dimensional point of view. But it's a huge, huge shrink rate. Really is.
So, if I understand, let's say the powder, okay, the feedstock is heated up in the barrel, already put under pressure, pushed into the mold, etc. So then it typically is allowed to cool down anyway, to solidify, okay, but then it needs to be heated up again at high temperature, a much higher temperature actually, to get this effect, this special extra bonding, deeper bonding, and that achieves a very, very high shrinkage rate. Okay, here, that's quite scary, thinking of, dimensional stability, dimensional control, right? Can designers actually predict, okay, with this material and with all these process parameters, we know it's going to be whatever, let's say 18% reduction in dimensions, and like in all dimensions equally, right? Is this something that's relatively predictable?
It is, yeah. During that sintering sort of stage, which is the high temperature processing stage, you can actually predict based upon the material that you're using. Now, the material that you're using, like polymers, like the standard injection mold machine, you'll get a sort of data sheet that comes with your particular sort of feedstock, and they'll say, okay, this is 16.25% rate upon sort of sintering or post sintering. So the data is very solid and predictable, such that when we're creating the designs from a designer's point of view, you need to make sure, or from a tooling point of view, the toolmaker needs to take in consideration the shrink rate, or sort of the additional material that needs to be added into the cavity in order to create the final part after sintering. So that is very, very predictable and repeatable. However, it's, again, I must reiterate that depending on what the product is and where that goes into the final assembly will determine whether any part needs to be post-processed. In other words, polished or additional machining or additional sort of threaded components, tapped or whatever inserts need to be sort of added on to that post-processing step.
Sure. Yeah, right. The first time I saw this process was, maybe 8 years ago when I visited the Luxottica plant in Dongguan. Actually, they have two plants, let's say. It was roughly 6,000 people each. And one of them was just for metal parts. And they were doing some metal injection molding there for some small parts. I mean, as one could imagine, is for eyewear, right? For frames, glass frames. So, and it was relatively small parts, close to the hinge, need to be high, how to say, dimensionally very accurate, because if it's a bit off, then the hinge will go a bit off, and then the way the whole eyewear frame will open and everything would, the way it would hold on somebody's face would be a bit different, right? So they were using it on some parts with high precision requirements. However, they were also doing some post-processing. They were not just, boom, let's make it in that grade of steel and, do the demolding and sintering and everything. Sorry, debinding and then sintering. And let's just use it like that. Now they were doing some kind of plating and some other surface treatment for aesthetic reasons. So that's quite common also. Okay, and then if we summarize, basically, you have thermoplastic injection molding, which is what most people think about when they hear injection molding. It's plastic that melts and then solidifies when it cools down. But metal injection molding is actually a mixture of a metal powder and some kind of binder. Okay, I get that. And there's some extra processes, as you mentioned. After injection molding and demolding, there's debinding and sintering. Okay, that's clear. Now let's compare that with casting, because I think most product designers will think, okay, well, so when does it make sense to use MEM, metal injection molding, versus some kind of casting, right? What do you think about this? What are the key advantages of MEM?
Yeah, no, that's a really good question. And from a designer's point of view, this is something you need to look at with respect to what is the best process. Now, not everybody's aware of the MIM process or the MIM process. Naturally migrate towards casting of some sort. Call it high pressure die casting, which is the most common high engineering sort of process available. However, you've got to look at the advantages or disadvantages compared to the process itself. Now, generally, when I've used casting or high pressure die casting processes for various different components, they have come out with a set of limitations, let's say. And I think the biggest one there is the porosity. So when it comes to the casting, it's renowned for having voids and other issues surrounding porosity. Again, you really got to look at and analyze the end use of whatever you're designing. Now, casting may be the option. However, today we're looking at sort of the options with respect to MIM and can that compare and can it compete? Well, the answer is yes, it can compete. One is a very, very quick process with respect to the injection part, but we've still got some post-processing, which we've already talked about, as in the deep binding and the sintering, and then the post-processing after that, as in the finishing and stuff like this. So when it comes to the limitations, so there's certainly limitations on the MIM process itself, but I would say there's more so on the casting side of it, simply because it's a lot heavier, what I call a heavier industrial process. It's not a clean process, whereas I call the MIM a cleaner process, similar to the injection molded process. So that is that side of it. It's the cost that comes into it. Well, both of these processes need the steel tooling, so there's comparisons there. But I would say it's the geometry you're looking at. Sometimes there's more limitations on the casting side versus the MIM, because with the MIM you can certainly look at the similar style of complexity with respect to any of the injection molded parts. So there's that. And another one we're looking at, I guess, is the accuracy and the tolerances of the finished part itself. Now, we've already discussed this huge shrink rate, but it is very predictable and controllable for the MIM process, whereas a casting does seem to have less certainty and predictability from a cooling as the part comes out of the die cast itself. The cooling process does tend to wander a little bit from a tolerance point of view. That's certainly my experience. Certainly my experience that I've seen. And anything that goes into a final product that requires bearings or other high precision components to be mated with those castings, for sure, 100%, you need to do that post-processing and finishing. Whereas on the MIM, that's questionable whether some of those processes are required, simply because you can get a better and higher predictability from a out of tool tolerance point of view.
Right.
Okay, so we certainly have that. So the dimensional variability, I would say, is greater with casting than it is over MIM, for sure. And the other massive one, I think, is material availability. Yeah, when we're talking about castings, it's I can't list 10 materials off the top of my head where I could certainly have a lot more materials that are available for the MIM process, giving that the designer a lot more flexibility from an end use point of view.
Right.
Sure.
Most cast products that I've seen have been either aluminum or zinc. There's a few more, but it's definitely, and that was mostly for high pressure die casting, right?
Yes.
With the types of products that we get involved with, that's the vast majority of cast parts, right? They're high pressure die cast, and usually it's aluminum or zinc. So what you're saying is that with MIM, there's a much wider range of metals. It could be various grades of steel, basically, also.
Oh, for sure. Yeah. Definitely.
Yeah.
It's sort of the steels that can be used. You've got a lot of different alloys that can be used from the ferrous aspects, so as in the steel side of things. So you've got low sort of grade. You've got high grade alloys you can use. You can use, all the different standard carbon steels, looking at various different strengths and ductilities and stuff like this, which I guess is a relatively true from a casting point of view. However, we're looking at a lot of more, I would say there's more advantages for MIM from a material point of view. Now, we talked about ferrous steels, we're talking about tungsten, we're talking about stainless steel, we're talking about cobalt, we're talking about all of the, I would say, high engineering materials that can be used with this MIM process. And for certainly that you've definitely got limitations when it comes to casting from that point of view.
Right. And some relatively, some metals that are in fashion, right? Like titanium and things like that. Yeah.
True. Yes. Yeah.
Right.
Yeah, absolutely. So there's certainly a trend when it comes to material selection, let's say, in certain industries.
Right.
Yeah, for sure.
So what types of industries tend to use MIM the most so far?
Some of the industries that are using them, jewelry comes to mind, simply because this is a high-end material selection. We've already talked about titanium. Some of these higher, in-trend materials can be used there. The material can be highly polished and really intricate components coming out there at the moment. So that's one. Another big one is the medical industry. When we're talking about medical industry, we're talking about implants and in-body components. My mum, bless her, coming over here very shortly, she's had various different hip replacements, knee replacements multiple times, and some of those have been like, sort of cast components, out of titanium. The technology these days is incredible. So medical implants is a big thing. Some of these exotic materials as well can be used in the aerospace industry. Let's talk about the automotive and the speed at which the innovation is moving forward these days, particularly in China, as you and I know. Renaud, the car industry is not a slow moving industry, and some of the
Not these days.
material, yeah, correct, yeah, and some of the materials that are required, particularly if we look at some, not just the car industry, but electric vehicles, let's say, because we've got the heavyweight batteries, a lot of the components in there elsewhere needs to be potentially weight conscious if we're trying to, or some of the companies out there trying to get a performance vehicle. All of this takes, material selection into consideration, as well as the process on how to actually create some of these exotic shapes and materials that go into some of these fantastic designs that we're working on. Another one that comes to mind that I've had a conversation with someone about this is firearms. Not my area of expertise. I'll put my hand up there. However, it is one of those things that does generally tend to think, MIM process, it's a small component. I need this. I don't really want a die casting, for this. Machining doesn't make sense, but MIM is perfect for this type of sort of component or small, intricate, high complexity sort of parts.
Right. And then general consumer goods. Again, you design you design a new product, because out of this, medical, aerospace, and so on, people might be thinking, whoa, okay, that must be quite an expensive proposition. However, when you need, especially, I think, parts that are not very large, but that have a geometry that's a bit tricky, a bit challenging, and it needs to be high accuracy, right? Would you say that usually for metal parts like this, MIM, deserves to be studied?
Absolutely. 100% totally agree with you there. Yes. And it's something that we deal with on a daily basis, is the consumer electronics products and the designs that come through our desk, but come past or on our desks on a day-to-day basis. Some of the components would be very well suited for this process, MIM. And it's something that really should be looked at, I would say, more than what it is at the moment, simply because I think this is a very overlooked process, or not as widestream or mainstream, let's say, as machining, or just try to find some exotic polymers that will be used in injection molding. A lot of people overlook the MIM process simply because it's not as mainstream, it's not as in front of you as what it should be and could be.
Right. And sometimes, again, as I was saying, some relatively intricate geometries, well, if you can do that, you might actually replace 2, 3, 4 different parts with one part made with MIM. And then suddenly, okay, that part, the unit cost might be a bit higher than, what you think you would deserve. However, when you look at the overall thing, so you have, fewer moving parts, faster assembly, of course, you cut costs in a lot of places, just one mold, etc., etc. At the end of the day, this might actually save you quite a bit of money, but this is more, again, for relatively small parts, because larger parts, again, obviously require larger molds, but also when it has to go into the furnace, into this 1200 degree sintering process, well, you can fit a lot of small parts, but not so many big parts. So all of these costs basically pile up. So it is usually more suitable for relatively small parts, small and medium-sized part, let's say, right? Does that make sense?
Yeah. I would say that that's relatively sort of a true statement. Obviously, there are extremes either end of the scale, but yeah, the majority of the components here would be on a small to medium size, for sure.
Right.
And another thing that I just thought of on this point of view is, you're looking at the material choice, and as a designer, you've gone with the best option for you from a polymer point of view, and you put your product together, or the customers put the product together, for example, and they started to do some testing. Reliability testing shows there's a weakness in one of the components, which is made of sort of one of the best engineering polymers out there. And what do? We need to go back and we need to evaluate and understand the failure points and the failure modes for that particular part. And it may be that the material selection could be switched out to one of the metal components that could actually come out of the MIM process, which could resolve all of the issues, as opposed to going back to the drawing board. Okay, this small mechanism here is relatively small. It needs to be small simply because it's got the space constraints. So, and it may take an awful long time in order to re-engineer or rethink that particular area of weakness in the design and keep it as plastic instead of, you know what, I'll keep it exactly the same, but I'll just make it out of metal. We'll go down the MIM route. That may resolve all of the problems. So again, there's something that designers should be aware of from a process point of view,
Right.
such that they can, all of a sudden now we're analyzing some of the engineering polymers from a strength point of view, from a stress point of view, elongation point of view, whatever the case may be, as from a design point of view. All of a sudden we're putting metal into the mix, and that may be the key factor with respect to, does this product work or not?
Yeah, right. So when selecting material in general, so you kind of prepared some notes before the call. We just have about 5 minutes left. So a few things that you wrote also were, when it comes to material selection, obviously the typical mechanical, physical properties, strength, ductility, hardness, etc., are important. In some cases also chemical properties like resistance to corrosion, oxidation, etc., obviously cost, but also processability if there needs to be maybe some CNC machining after that, right? So this is, let's say, general advice for product designers. The last topic maybe that we can cover quickly is, what about the equipment typically needed? So we touched a little bit on that. You mentioned that, let's say, typical plastic injection molding presses, if the barrel is changed, or at least the screw and some of the key components are changed, are adjusted specifically for MIM, yeah, these kinds of presses can be used, no problem, and it's quite common, right?
Correct.
What other type of equipment is needed to do some MIM?
Well, we'll step back to the process. Step one, which we talked about sort of previously, is this mixing. Now, you can't just do that in a hand mixer or in a bowl and just someone stirring it. That needs to be, mixed correctly. So there's generally mixers available for this process itself. So that's the first thing. We'll talk about the injection mold machine, where it's basically a standard injection mold machine. So you're looking at your 25 ton, 200 ton, whatever machine size is required. However, you would need to generally do that upgrade that you just mentioned on the screw, because of the abrasiveness of the feedstock going through that has that metal in it. But then that's when we sort of start to switch out. Once we've got that part out, we need to then look at the two specific pieces of equipment for the MIM process. Now, the first one there, past that injection process, is the debinding equipment. Now, we talked about how to do that previously, either heating it up or with a solvent and stuff like this. So depending on what your feedstock is, will require, whether it's wax or a polymer or some other binder, will require its own specific process in order to remove that binder. So you're looking at thermal debinding. You will need an oven in order to do that. So you need that heating apparatus or the equipment specifically for that debinding process, where it tends to evaporate or decompose from that, we call them the green stock or the brown part that comes out of your injection machine. Okay, remember, this can't be used, and it's way oversized. Remember that, it's 16 to 20, maybe even more oversized. And this is because that has that carrier or that binder included in it at this moment in time.
Right.
If you're going into a solvent, obviously you need a solvent bath. Generally, the solvents are heated up and it's agitated at the same time. So it's not a case of like just dumping it in some water or a tank of water. So you would need that special equipment. And if it's a solvent, it needs to be contained into a certain area. So it's nice and safe, and extraction fans and everything like this. So, bear that in mind, please, team. So you got the debinding equipment. After that, you would need that sort of high temperature furnace for the sintering process. And this is like the key aspects of this. Once you've got that high furnace in there, it's generally put through on a conveyor. So it moves through, similar to the PCB sort of reflow oven or something like that. So it goes through. It's not just sat in the furnace. It generally goes through a moving furnace. This furnace is a high temperature, but it's also a controlled temperature. Okay, so this is really important, such that these metal particles, let's say, do fuse together, like I was explaining before, going from those, perfectly round spheres where we've got the point-to-point contact into a sort of a lot more stable and predictable and strong component. And again, furnaces do come with a lot of control required, basically from it's not a safe place to be around. So you need to make it safe, make sure it's in the right area, you got all the extraction equipment in place and everything like this. So it's not just getting a couple of little bits extra. This is a very, very specific setup required for the MIM process. So if you're thinking about getting into it, probably best go with a supplier that is already set up for the MIM process and use them instead of trying to bring that in-house.
Yeah, of course. Yeah, right.
So for sure. So, we're looking very, very different from a standard injection mold shop to an MIM shop or metal injection mold shop. Very, very different layout, very, very different sets of equipment required for the production line itself.
Right. All right. Well, that was very nicely covered. Thanks a lot, Paul.
All right.
I think the listeners have if they hung up until the end, they really have a much better idea about what MIM can do for them. Hopefully. Otherwise, please send us some messages if we missed something. Okay. Thanks so much for sharing this today.
Pleasure. All right. Talk again soon.
Yeah, and thanks to the listeners. And as always, you will hear from us next week. All right. Till next time.
Thanks again for listening to this podcast brought to you by the Sofeast Group. We're on a mission to provide you with everything you need to manufacture effectively in Asia, including inspections, auditing, new product development support, contract manufacturing, 3PL warehousing and fulfillment, and much, much more across Asia's key manufacturing areas. Visit us at sofeast.com, that's SOFEAST.com, to learn more and get help. If you've enjoyed the podcast today, please do rate, review and share, because it will really help others discover us too.